the first step in calibrating the record alignment of the tape machine after you've adjusted the azimuth so that the azimuth is correct and corresponds between the record and playback heads is to adjust the bias on the machine. So I thought it was important to tell you and demonstrate and show you how the bias interacts with the other record electronics and the interface between the tape and the machine. As we discussed, without bias, the tape is very difficult to record on. The domains tend to stay put. So if I make a little chart here that shows you as we increase the bias current here, what the behavior of the machine is in different conditions. So, and this would be, on the vertical axis would be an increase in level on tape. This is not calibrated in any way, but it's meant to be illustrative. So, if we have very low bias, and I'm recording a nominal signal, either a broadband signal or, say, a mid-frequency tone of, say, 1,000 hertz, as we increase the bias, you get an increase in sensitivity, and that is the level will increase up to a certain point, at which point the level sort of plateaus, and you don't really get much more signal level beyond that point. And then as you increase the bias, you'll actually get into a condition of overbias, and it'll start to lose sensitivity. So this black line represents nominal recording level, that is say a wideband frequency, like a wideband signal like white noise, or a mid-frequency tone, say 1,000 hertz. In addition to that, the tape is slightly nonlinear in that high frequencies respond differently to bias than low frequencies. So if I were to plot the sensitivity of a high frequency signal relative to the broadband signal or a mid-frequency signal over the same change in bias, you would see that the high frequency signal would get much, much louder at a certain point and then begin to fall off, and then fall off precipitously. So as you increase the bias, the general sensitivity of the tape goes up to a certain point and then reaches a plateau. Somewhere on that plateau will be maximum sensitivity for high frequencies. Let's say that this is the plot of a 10 kilohertz tone. The 10 kilohertz signal will get to its peak point at a certain point on that plateau of general sensitivity and then begin to fall off. And now, a third characteristic would be the noise performance of the machine. That is, the distortion component, the second harmonic and other distortions, and the background noise of the tape, relative to the signal level, are also affected by bias. So if we start from a position of no bias, there's relatively little signal and relatively high noise. So the noise performance of the machine is going to be very poor. You're going to have a very high noise level, right? Then the noise performance will improve as bias increases, and you'll get to a point where the noise and distortion are at a minimum. And then as you increase the bias, noise and distortion will start to come up again. So you'll see that there's a single point of critical bias where you're on the plateau of general maximum sensitivity of the tape, where you still have reasonably high frequency sensitivity, but the noise and distortion components are at a minimum. And that point right there is what I'm describing. Actually, I've indicated that poorly. But that point right there is what we're describing. Right there. Where the noise and distortion components are at a minimum, you're still on the plateau of general sensitivity, and the high frequency response is still reasonably good. That point, the point of lowest noise and distortion, will always be past the point of peak sensitivity of high frequency response. So if you find this point, that is this bias point, and then find this point, the point of minimum distortion, at that point you will see that there is the point of minimum distortion being past the point of peak sensitivity of the high frequency response. If you draw that point over here, you'll see there's a difference in the high frequency response between that point here and that point here. And that difference can be used to calibrate the machine. That is, that difference can be used to find the point of minimum noise and distortion. And that can be described in terms of decibels. That is, you increase the bias on the machine until you find the peak sensitivity at a known frequency, say 10 kilohertz or 20 kilohertz. And then you increase the bias until it drops by this amount, and you will have found the bias point of minimum noise and distortion. And that's the critical bias or optimum bias for your tape machine. That point is going to be different depending on the geometry of the heads, that is the width of the head gap on the heads and the formulation of the tape. These values are published, so for example, for any kind of tape you can find the recommended amount of overbias, and this figure is described as overbias. So for example, if this is a 10 kilohertz tone and you find that at a given speed, say 15 inches a second, you reach the point of minimum noise and distortion when you've lost 2 dB of sensitivity in the high frequency tone, then you would describe that as 2 dB of overbias at 10 kilohertz. And that would allow you to find the optimum bias point for that tape machine. These figures, the overbias figures for every tape and every head manufacturer, are published, and you can refer to those published tables. Most of them are available on the internet. But it is also possible to find that critical bias point by ear. And the way you would do that is by setting the machine up to record a low frequency tone. And I say low frequency because low frequencies it's easy to differentiate between the noise and distortion components and the signal when you're listening to a low frequency tone. So you could set the machine up to be recording, say, a 30 or 40 hertz tone, and then gradually increase the bias, and you will hear the noise floor begin to drop. You'll hear the noise and distortion components of that low frequency tone disappearing, and they'll reach a null point, and then as you increase the bias you'll hear them increasing again. And you'll just rock the bias control back and forth until you've satisfied yourself that you've found that point, the low point on that curve of the noise and distortion components, and you will have found the optimum bias point for that tape. And what you can do then is, having found the optimum bias point, you can then plug in a 10 kilohertz tone or 20 kilohertz tone and adjust the bias down until that signal is at a peak, and record those two numbers, and you will have found your personal overbias for optimum noise and distortion on your machine with that tape formulation. And that can be used with any tape on any machine. That is, if you find yourself with a tape machine and a reel of unknown origin and you need to record on it, you don't know who made the tape, or you have no access to the information about the machine that would describe the head gap, so you couldn't find a published spec for it. Using the noise and distortion characteristic of the machine is a way to find optimum bias on that machine with no other tools. If you have an oscillator and a tape machine, you can find the optimum bias point for any tape. Okay, so I'm recording a 20 kilohertz tone on the machine here, and I'm going to adjust the bias to correspond with our in-house standard, which we've derived from the noise performance of this machine. And our in-house standard is 3 dB of overbias at 20 kilohertz. So for this alignment, I'm going to use the master bias control to align the left channel, and I'm going to use the individual channel control to align the right channel. And then the next time I align the machine, I might do it the other way around. The important thing is that all of these pots are being exercised over the life of the machine, and you don't end up with pots that are stagnant in one position and develop poor contact as a result. So I'm going to record the 20 kilohertz tone, and I'm going to adjust the master bias trim pot so that we get peak level. And the peak level here is quite high on the scale. So I'm going to adjust the output of the machine using the non-calibrated output so that the peak is resting at 0. And here you can see I've found the peak. If I increase the bias, the signal drops. If I decrease the bias from that point, the signal drops. So I'm going to start increasing the bias from this point until we get to minus 3 dB, which is the point that we've found at 20 kilohertz corresponds to lowest noise and distortion on this machine. So I am now calibrated on the left side. So I'll put this machine back into the calibrated output, and I'll do the same on the right, but I'll use the individual channel trim pot here. Some machines don't have a master bias control available, or if they do, it's an internal adjustment. So in those cases, you just use the channel alignment pots and don't worry about it. Same deal here. I'm adjusting the non-calibrated output so that I can keep the peak signal at about 0 on the meter, and that allows me to find the minus 3 dB point easier. So now if I increase the bias, if I decrease the bias, the signal level goes down. If I increase the bias, the signal level goes down. So I'm satisfied that I found the peak, and I'm going to increase the bias until the meter reads minus 3 dB. And that is now calibrated for bias.